the course participants and our respected dignitaries available over here in the inaugural program. So today we are going to start this SETU program, which is on space technology and applications. So first of all, I would like to request Dr. Anil Kumar for the welcome address.
Good morning to all. Dr. Kiran sir, Dr. R.P. Singh, Director IIRS, Dean Academics, Dr. Harish Karnatak, and my dear all participants. I welcome you all for attending this very important grassroots level program initiated by ISRO, basically for school teachers which are working at grassroots level for the kids, which are the very starved for the country to get enabled about this technology, and these teachers will be working as a secondary source. So again, I welcome for all the participants and all the teachers for joining this course, and I request that they can start maybe small elective, small paper, small activities to the students in the school level. Thank you.
Thank you very much, sir. Now I request our Dean, Srimati Sefali Agarwal Madam, for the address on training and education activities of IIRS.
Thank you, Dr. Kamal. Kiran Kumar sir, former Chairman ISRO and Member Space Commission, Director IIRS, Dr. R.P. Singh, Dr. Anil, Dr. Harish, Dr. Kamal, and the school teachers who have joined us from all across the country. A very warm welcome from my side to this program on SETU, which is Space Education, Training and Knowledge Upgradation. The word SETU, it means a bridge, and it beautifully captures the purpose of this program. It's a bridge between curiosity and knowledge, between classroom and exciting world of space science, and between educators and experts who are working in this field. So the lectures would be given by the experts who are directly working in this area. So as teachers, you all play a very important role in the society. Your influence extends far beyond textbooks. Every day you inspire students, you inspire curiosity in them, you nurture confidence in them, you shape their values and help these young minds discover their potential. So the future scientists or engineers, innovators or leaders of the country are sitting in your classrooms. With this concept in mind, the course has been designed to strengthen your understanding of space science, space technology, and their applications so that you can bring these fascinating concepts into your classrooms and inspire the next generation. You can teach them, you can inspire them in this area, in this field of space science. So the program is being conducted through the IIRS Distance Learning Program, which is an online initiative of the Institute of IIRS, which was conceptualized way back in 2007. And the objective of the distance learning program is to build capacities in the field of space science, remote sensing, geoinformatics, and its application by making quality education accessible to a wide audience. And over the years, we have been training in this field. A large number of participants have benefited in this online platform. Along with this, IIRS also offers offline programs in the field of geospatial technologies, remote sensing, GIS, GNSS, and its application in our campus. And for both online and offline programs, our course brochures are available on the website. So you can have a glimpse of it and come to understand what are the courses being offered by the Institute. Today, around 831 participants have joined this program. So the enthusiastic response reflects the interest among the educators in the country in integrating space science into their school curriculum. Over the coming sessions, I encourage all of you to participate, actively interact, ask questions, share your experience, and explore the knowledge gained here. I hope the knowledge gained here can enrich you and help you in your teaching the students. I thank each one of you to show your interest and taking the time and joining this program. I hope you have an enjoyable and an enriching experience. Once again, welcome you all for this program. Thank you.
Thank you very much, madam, for the brief introduction about the training and education activities of IIRS. I hope our participants have a glimpse of all these activities. Rightly you said, participants are requested to please ask the questions. So now I request Dr. Harish Karnatak, Course Director and Head GIDDL, for a brief about the course overview of SETU 2026.
Thank you, Dr. Kamal. Most respected Kiran Kumar sir, Director IIRS, Dr. R.P. Singh sir, Dean Academic, Shefali Madam, Dr. Anil Kumar, Group Head, Geospatial Technology and Outreach Program Group, and my colleagues here. This SETU program, this is a 2026 edition. So here, just I will brief you about the registration and the participant, what we have. So as you can see here, this year 960 participants have registered for this program, and this is a sixth edition what we are conducting for the school teacher. So last 6 years we are maintaining the similar kind of topic, but I hope now in the next year we'll try to change that topic in the theme mode. So this year the title of this program, what we announce, is Space Technology and Applications. So as you can see here, the teachers, basically those are teaching science, mathematics, geography, basically as a subject from class 9 to 12 are basically invited to join this program. And here you can see the distribution of the participant. Around 50% teachers are telling they are teaching the science as a subject, and 16% teachers are teaching mathematics, and 10% teachers are teaching geography. Other side, the teacher, those are not teaching the science as a subject, but they are teaching some other subject, are also shown the interest in the program. This number is around 24%. If you see the distribution of the participant, here the you can see the CBSE board is a major share here. Around 60% teachers are from the CBSE board, and the state board around 23%, and we have the ICC board around 2%, and 16% teachers are telling that they are teaching basically coming from different board. We have a good representation from the states and union territory in the country. And now if you see the course content, what we are going to deliver, in this course generally we invite the senior scientists from ISRO centers. Generally they are the directors of the ISRO centers. This year also we invite Dr. A.S. Kiran Kumar, former Secretary Department of Space and former Chairman ISRO, to give the lead talk on the SETU 2026. Today he'll be talking about the Indian space program. After that, today afternoon, the second session will be on satellite communication and navigation payloads, technologies and application. Here Dr. S.C. Bera, Outstanding Scientist, Space Application Center, Ahmedabad, will be basically taking this session. Then tomorrow we'll be talking about the satellites and spacecraft system. This is another very important topic. We invite the faculty from URO Satellite Center, URSC Bangalore, Sri S. Sudhakar. He's a distinguished scientist and Deputy Director URSC. He will be delivering this talk. Then we'll have the next session on India space program and future challenges and opportunities. This session will be delivered by Scientific Secretary ISRO, Sri M. Ganesh Pillai. He'll be taking this session on 9th June, that is tomorrow. Then we will have another important topic by Director Space or Science Program Office ISRO Headquarters, Dr. T.P. Das. He has selected a very interesting topic. He told that he'll be only talking about a topic on a message to the student from ISRO. So this is the topic what he has selected this time. So he'll be talking about it on 10th June. Then satellite remote sensing technology and its application, Dr. Sushil Kumar Srivastava, Outstanding Scientist and Associate Director NRSC, will be taking this session on 10th June. Then we'll have the next topic on the launch vehicle systems. It will be from Vikram Sarabhai Space Center, ISRO, Thiruvananthapuram. Then we'll have the space science and Indian space exploration system. Dr. Anil Bharadwaj, he's a director, PRL Ahmedabad. He'll be taking this session on 11th June. 12th June, we'll have the very important topic by STREC, ISRO Bangalore. That will be on space situational awareness. Then we'll have the future space exploration and space tourism by Dr. D.K. Singh, Director, Human Space Flight Center, ISRO, Bangalore. So this is a total overall program what we are planning. Since in this program, the senior scientists or the senior management level scientists are taking the sessions, so sometime there may be slightly change or rescheduling in the program. I request all the teachers, please cooperate in the change, because it is due to their availability, or suddenly some meetings are coming, or their presence is required in some other place. So sometime we have to reschedule the this program. So with this, I thank all the teachers and for their interest in the program. The SOPs and guidelines for the course are already shared by our team. I request all of you, please go through it. Generally, we will make this session live through the YouTube channels, through our e-class platform, and also learning management system. As per their choice, they can choose it, and end of the each session there will be one quiz. So I request all the teachers to participate in the quiz as well. So that's all from my side. Wish you very all the best for very interesting and innovative learning during this week. Thank you very much.
Thank you very much, sir, for your brief introduction about the course Setu 2026. I hope all the doubts are cleared by this session. What are those sessions? Who will be taking all those classes? So that all have been covered during this address by our Dr. Harish Chandra Karnatak, sir. Now I request Director IIRS, Dr. R.P. Singh, sir, for his welcome address.
Thank you, Dr. Kumar. Good morning to all. Respected Sri S. Kiran Kumar, sir, Chairman, Apex Science Board, and former Chairman of ISRO, seniors of ISRO, faculty members, and dear participants, the school teachers who are joining us from different parts of the country. Greeting from IIRS and welcome to SETU program 2026. IIRS is an institute which is working in the field of capacity building and training since 1966, and provides different trainings and education in the different sectors of education, like school, the universities. So we conduct trainings for the school students, the Yuvika, you are must be knowing the important program, the teacher, the Setu, the university professors, university students, and the government officials. Setu program is the dedicated space educators training and knowledge upgradation program for school students. And here we aim to see that whatever the technology is being developed at ISRO over the time, because this field is continuously changing, and a lot of development is taking place. Our school students and teachers should know them so that they become the part of the curriculum at a school level, so that the school students know what are the development happening in country, so they can choose their career path as well, get motivated to join this program. So we believe that school is a building block of education, and all technology which our country is going through, which is space technology, one of the frontier technology, students should know. And this is how this program to school teachers will help us propagating the ideas to the school level. And that's the basic motto of this particular SETU program. As told by Dr. Harish, it is 6th version of it, and we would like to continuously upgrade, and would like to be creative. So even we will request your feedbacks on this line after the course, that what are the things we can change, so that our the dialogue, the communication between the scientists who are really dealing the subject and the young students who are studying in the school, the communication continues. I take this opportunity to thank all the seniors who have agreed to give the talk in this sessions of Setu. I'm particularly, especially very thankful to Sri Kiran Kumar sir, who always motivates us as well as the student community to see that the technology is seen or visualized, and the students are engaged into the fundamental knowledge of the technology. And sir has agreed to give inaugural talk. He will talking about the space program, and sir has been the scientist who has actually developed most of these systems, which has over the 30 to 40 years, you have seen whatever you call ISRO, various satellite programs. He has been the administrator in his capacity and up to the directors and chairman level. And sir has agreed even to talk to school teachers today. So I understand that it will be an exciting session where sir will be talking about various developmental aspects of space science. I again am very thankful to sir for agreeing to give this talk, and I also take opportunity to for all the faculty members of IIRS organizers who arranges this program every year, and I wish that this program becomes successful and we evolve ourselves through your feedbacks so that we can do much better programs and communicate science at the grassroots level to the high technology level. Thank you very much.
Thank you very much, sir, for your motivational address towards our participants. Indeed, Kiran Kumar, sir, all our participants are eagerly waiting to listen from Dr. A.S. Kiran Kumar, sir. Indeed, again, one of the point which Director sir rose, that the feedback. Yeah, I urge from all the participants to please provide your feedback so that this program can be further enhanced. Now, I request our chief guest for the inaugural address, Dr. A.S. Kiran Kumar, to address our participants. Sir.
Good morning to all of you. Thank you for this opportunity. Good morning to R.P. Singh, Director IIRS, Harish Karnatak, Shefali Madam, Kamal Pandeji, and all of you. And more than that, all the participants from across the country. What we saw actually the pie chart really indicating the spread and the interest that is being shown from across the teams. And as this is also the sixth program of this kind, which has been organized by IIRS. So let me compliment IIRS also for persevering on this and then making it more and more useful. And as we progress, make it more vibrant. So today, as you are seeing, India is moving ahead in using space technology for various activities, and starting from the early days when we got our independence to now, the way space technology has transformed many domains of life on Earth or life for India. It's quite amazing. I'll touch upon the details in a subsequent lecture, but right now I just want to bring to your awareness that the society keeps changing the way it lives depending on the technological tools that become available. And these tools continue to change the thought processes and also the manner in which we interact both within a state, country, or across the countries. And space being a frontier, which gives you an ability to go beyond Earth and then look at Earth from outside. So it's only when you are able to look at yourself from beyond, can you see the problems that are present and then also figure out what way you can make changes in the way you are doing things. And space in a way provided such an opportunity when humans realized that they can build some mechanisms to take them out of Earth and then place them beyond Earth to look at what is happening on Earth. This is the one which really changed the way, for example, that weather monitoring and weather predictions happened is primarily because of our ability to look at Earth from space. In a similar manner, while you are restricted in knowing what is happening around you, if you go to space, you can see what is happening across the globe. So not only it gives you a perspective of what is happening in the total globe, but also it erases many of the borders and boundaries which we have created while we survive on Earth. So in many ways, the ability to go to space makes a huge difference. And humanity, as you can easily visualize, has always been fascinated by what is happening in space, what are these celestial bodies, is there any correlation between them, how to understand this universe. In all this, while in the earlier millennia, much of the effort was based on human ability to make observations, humans gradually built tools which help them look at the entire universe in very different domains, expanding the horizons of their sensors. And today you're seeing that humans are talking about going to other planetary bodies and even setting up the habitation centers there, etc. But what is it that we are trying to attempt in this particular program, Setu? What is being attempted is that each generation needs to understand what has happened, how things are changing, and how rapidly science and technology is impacting the society. And if we have to make a difference to tomorrow's world, it is only when we bring in the next generation an awareness of what has been done so far, and also make them look at beyond today's problems, look at future scenarios, and throw open to them a challenge. And for that, we have to open the windows. And this program, the school teachers are actually in an excellent position to carry out this activity because they are directly in contact with the next generation. And it is through your efforts that how a child evolves into an adult and then a citizen of both a state, country, or even the planet itself. And it is in this context that Indian Institute of Remote Sensing, along with the Department of Space, is trying to put together information on how India has dealt with the problem so far, and also showcase how things are going to move ahead. And in this process, definitely the need to build information sets, bringing it to your awareness is the first step. And of course, what you also need to look at is look at books which portray this information, and also many videos. And if you can also create projects using the data collected from satellites or space-based observation, and bring in the process of experiential learning to actually quench the thirst of curiosity that a child has, then the process, what is being attempted in this Setu, of bringing to your awareness what India has been doing in the space technology, and then also address issues that are going to crop up for future, and in a way ignite the thought processes of the young minds, making them feel that we need to understand the environment in which we live, the universe in which we live. What is our ability to comprehend that? And do we have any ability to impact what is happening in the environment or the universe and make changes? So this is a holistic attempt of looking at space from our own vantage point. And let me compliment IIRS for bringing this concept and into reality and attempting to reach out to you. And during the course of this program, you will have many opportunities to interact with those who have actually put their hands, dirtied their hands in carrying out this work. And through their experience, you can gain some information which will help you mold the next generation. One, we need to quench their curiosity, but also we need to ensure that they become more curious and they start addressing the problems they are facing. So if we are able to do both these things, on one side, bring them information of what has happened, and then make them realize that they will be the architects of tomorrow's existence on both on planet Earth and in the universe. So thanks for this opportunity to inaugurate this unique program, and wish all the participants a great many days of learning, using which you can carry out the next task of bringing this information to the students with whom you are going to come in contact. Wish you all the very best.
Thank you very much, sir, for that address, while motivating all the participants who are the direct bridge between the curious young minds and the techno experts in the space technology. Our participants are eagerly waiting for the session from your side also. soon after this. This was only a glimpse for all the participants. They are eagerly waiting for a new for the session that has to be delivered by you. Now, it's my privilege and honor to deliver the vote of thanks on behalf of the organizing team at this inaugural session of the special course for school teachers on space technology and its applications being conducted from June 8th to 12th, 2026. First and foremost, I would like to express our heartfelt thanks and gratitude to Dr. V. Narayanan, Chairman ISRO, for his visionary leadership and constant engagement that has made such an outreach program possible. I also thank a very heartfelt thank to our chief guest of this particular inaugural session, Dr. A.S. Kumar, former ISRO Chairman, for gracing this particular inaugural session. A sincere thank to Dr. R.P. Singh, Director IIRS, for facilitating the initiative aimed at empowering school teachers with knowledge in space technology and its wide-spreading applications. We are also deeply thankful to all our esteemed speakers who have accepted our invitation to share their expertise in this program. Your contribution will certainly enrich the leadership experience of our participants. We would especially thank to acknowledge Mrs. Sefali Agarwal, Group Director, Dean Academics, and Dr. Harish Karnatak, Head GITDL, for his overall coordination and consistent support in successful organization of this particular course. We extend our appreciations to group directors and group heads and heads of the departments at IIRS for their guidance and cooperation throughout the planning and execution of this particular program. To all the teachers who have registered and are participating in this course, we extend a very warm welcome. Your enthusiastic response reflects a strong commitment to bringing scientific learning into classroom across the country. Lastly, our heartfelt thanks to the staff of GITDL for making the logistic arrangement and ensuring the smooth conduct of this particular event. Once again, thank you all for being a part of this important educational journey. We look forward to a successful and enriching week ahead. Thank you very much.
So with this, we conclude our inaugural program. I request all the teachers to be here. We'll break for 5 minutes. Then we'll have the first session by Dr. A.S. Kumarji on Indian space program. So we'll break for 5 minutes and we'll come back. Thank you very much.
सर शुरू करें सर?
Yeah, I'm ready.
Okay. So good morning everybody. We are going to start our first lecture by Dr. A.S. Kiran Kumar sir on the topic of Indian Space Program. We are privileged to have sir on this session, and we are thankful to sir for agreeing to give his talk besides his busy schedules. So before sir start explaining his topic, I would like to introduce sir to all the audiences. Uh, Dr. Alur Srileen Kiran Kumar is a distinguished Indian space scientist renowned for his pivotal role in advancing India's space capabilities. He served as chairman of Indian Space Research Organization from January 2015 to January 2018. Kiran Kumar ji commenced his career at ISRO in 1975 by joining Space Application Center in Ahmedabad. He was instrumental in design and development of electro-optical imaging sensor for various Indian satellites, starting with Bhaskara series in 1979. His contribution extended to missions like INSAT 3D, ResourceSat, Cartosat, and Mars Orbiter mission, where he played a key role in developing critical payloads. Kiran Kumar sir has exemplary contribution and has been acknowledged through numerous awards like Padma Shri by Government of India in 2014, International Von Karman Wings Award in 2018, Chevalier Honoré National de la Légion d'Honneur France highest civilian award in 2019, ISRO Performance Excellence Award in 2008, Bhaskar Award by Indian Society of Remote Sensing 2007, Basvik Award in Electronic Science and Technology in 1998. Currently, Sir is a member of Space Commission and chair of ISRO Science Apex Board. So, with this brief introduction, now I request Kiran Kumar sir to start his talk. Thank you.
Thank you, RP, for that introduction, and good morning to all of the participants for this unique program where IIRS and ISRO is trying to reach out to the school teachers and through them make a difference to the way the next generation appreciates how India is performing in this space arena and how the future needs to be looked at. Now, if you look at India, see, you're all very familiar. India got its independence in 1947. And at that time, after many centuries of external rule, the tasks for the rulers were how to provide food, shelter, and education to its citizens. So that was the key task. And you can imagine in 1957, when humanity got a new technological capability of going beyond Earth. This happened due to the intense competition between the two superpowers of that time, America and Russia, who were trying to demonstrate who is more powerful and who is more capable. And at that time, Russians put an object called Sputnik into space in the year 1957. And you can imagine 1957 was just 10 years into independence for India, and the rulers struggling to provide food, shelter, and education to its citizens. Obviously, at that time, you can imagine if somebody were to go to the rulers of this country and tell them, we want to do some work in space arena, then you can easily visualize what would have been the response. But however, you need to really appreciate there were great visionary scientists like Dr. Vikram Sarabhai, Homi Bhabha, Satish Dhawan, etc., who were looking at how a country like India can benefit from the new technological developments that is happening. What is it that is going to make a difference when if you are able to go beyond Earth and put an object in space, one might ask. So you are all very familiar that from space, you can look back, look at Earth, and then if you are able to take an object to a place called geostationary orbit. Geostationary orbit is a location, a place at a height of 36,000 kilometers from Earth. And if you are able to put an object there, then it takes exactly 24 hours to go around Earth. And because Earth also rotates once about its own axis in 24 hours, the relative velocity between the satellite and an observer on the surface of Earth becomes zero. And as you can visualize, two trains on parallel tracks running at same speed almost appear stationary to each other. So in the same way, Dr. Sarabhai was aware that a great scientist like Arthur Clarke had pointed out that if you can put a transmitter at 36,000 kilometer, then you can look at one third of the globe and you can cover and do line of sight communication. So the idea of Dr. Sarabhai was in India in the late 50s and 60s, one of the key things was how to reach information to all its citizens. Just think of this as a possibility. If at that time, if someone were to tell something to others, how would it propagate to the entire population? In the early 60s, etc., India had a population of around 38 crore. And if you say something to three people, and those three people in turn tell something to another set of three people, you can do a simple calculation to find out how many cycles are required for all the 38 crore to get the information that is being talked about. So almost 17 cycles are required for information to reach. So Dr. Sarabhai pointed out that if you put a satellite at 36,000 kilometer, then the entire country can be provided with a broadcasting signal or communication signal which can be used. So with this in mind, Dr. Sarabhai started the activity of space program. And how did it start? In Tumba, near Trivandrum, India has a unique place called geomagnetic equator. So he could convince, Sarabhai could convince his friends across America, Russia, France, Germany, that if we do upper atmospheric research at this location of geomagnetic equator, it will be beneficial for the entire scientific community. So with that in mind, he could get sounding rockets from the friendly countries, brought it, and then got it assembled in Tumba and launched them to start the initial activities of space program. And even for doing this, he had to actually convince the fishermen of the region that's called Tumba, where a lot of fishermen in the beach are actually carrying on their activities. And Dr. Sarabhai had to convince them. He took the help of the priest of the church there, and with his help, he could get the permission from the fishermen that we can conduct these sounding rocket experiments, which will one day benefit the country. Starting with that experiment, India's like using the sounding rockets as a sort of a do-it-yourself kit. Today, you are all familiar. Atal Tinkering Labs or many do-it-yourself kits are available where children can be exposed to concepts by conducting simple experiments. Almost in a similar manner, India started its space program by bringing sounding rockets which were built elsewhere, got it assembled in Tumba, launched them, and with that learned the process of building our own launch vehicles. So one key thing that happened at that time was Dr. Sarabhai also convinced Americans, NASA, that they were building one of the most advanced technology satellites called ATSF, Advanced Technology Satellite 6 in the series, ABCDEF. And this satellite was carrying one of the largest antennas built at that time, almost 6-meter type of antenna. And this satellite carried to geostationary orbit, and from there it could broadcast signals. So Dr. Sarabhai convinced Americans and borrowed this geostationary satellite. You can easily visualize geostationary satellite if it is visible from America. At the same time, in India, we cannot see it because it is at a launch. We are exactly on the opposite side of the earth. So the satellite had to be moved over the Indian longitude, and Americans agreed to provide this satellite for use for 1 year. And India conducted an experiment called SITE, Satellite Instructional Television Experiment. The significant impact of this experiment was using this satellite carrying an advanced technology capability of broadcasting signals from satellite on ground. Today we are all familiar how we receive signals on our TV. What is a process called direct to home television. You have a 1 foot antenna on our rooftop, a small set-top box on our table. With that, our TV is able to receive the signal from the satellite directly and shows us video programs. Now you go back in time in 1975 when India conducted this experiment of SITE. What was done was borrowed the American satellite, moved over India, and for 1 year, ISRO, along with many other agencies in the country, broadcasted signals to 2,400 remote villages in 6 different states. And what was required for that? Instead of today's 1 foot antenna, it was a 10 foot antenna on the ground. Instead of a small set-top box, it was almost half a rack height of front-end hardware built at Ahmedabad, and then using black and white television set and programs created along with Doordarshan and Vivid Bharat, many of the Air India, that All India Radio, and using all these kinds of things for 1 year, India showed that it is possible to use satellite technology to reach information to the entire country. And now you can see what happens at the end of this experiment of 1 year, where in these 2,400 villages, programs were beamed on the television sets and the community, it was called direct to community sets. And you can also imagine in 75 how difficult it would be to reach to the remote places, make sure that power is available, equivalent of today's uninterrupted power supplies being provided there, and then through that program, broadcasting shown to the villagers. And then when this happened, and if you were to go to the powers that be in the Delhi and tell them what you are speaking now here in Delhi can be heard all over the country simultaneously. Now, do you think it requires a greater convincing for powers that be to understand that space technology is the way to go? And that's how INSAT program got approved. Of course, in between, you can see here, this event itself happened in 1975, and unfortunately we had lost Dr. Sarabhai in 71 itself. So though he had put the thoughts and then all the mechanisms he had brought in place, ISRO continued to work on his concept and made it a reality. And when India conducted this experiment, it was known as the world's largest socio-technological experiment, because you can also imagine at that point in time, only 4 metros had the privilege of seeing any television programs. They were Delhi, Bombay, Calcutta, Madras, and all the rest of the world, rest of the country had not seen any such thing. So with this, in 75, this experiment, government got convinced that if India were to move rapidly in disseminating information and linking the country, not only that, even weather monitoring. You can imagine from a geostationary platform, when you look at India and Indian subcontinent, and you take a series of pictures, say every few hours you take a picture. In each picture, you will get a cloud cover, and you can see by observing the cloud movement in the picture, you can determine the cloud motion vectors, and you can also measure a whole lot of parameters like temperature, humidity, and so many different aspects. And using such information, you can also predict weather in a better manner. Now here again, I want to bring to your awareness how use of space technology made a drastic change in the way the weather monitoring happened in the world. And you can imagine that if you want to get to know anything about weather monitoring and weather prediction, one of the thing is you need to have a good model for prediction. And that model, after it is realized, needs input at the starting point. So before the advent of space technology, only way information could be collected was on land, and there also where the observatories are set up. But Earth, almost two-thirds of the Earth is only water. And if you do not get any information over that region, no weather model can be very accurate. That's how, after humanity got the capability of going to space, they built sensors on the satellite which could observe what is happening over the ocean temperature, ocean wind vector, and a whole lot of parameters. And with these parameters being used, weather models started becoming better and better. That is how the humanity was able to get an improved weather monitoring. In India also, with the advent of INSAT series, one of the things that happened is it was possible to predict where and when a cyclone hits the coastline. You can imagine India has a coastline of almost 11,500 kilometers. In such a long coastline, whenever these cyclones hit the coast, it will impact in such a way that in the earlier decades, thousands, tens of thousands, 15,000, 20,000 people used to lose their lives because it was not known when it will hit. But then with weather monitoring and weather modeling become available, it is possible to tell where and when a cyclone will hit the coast. And today, because of this capability, in India, you have seen in the recent decade and a half, no super cyclone has resulted in loss of life in the ranges of what used to happen earlier. Now the loss of life has reduced to a single digit number. There also sometimes because some people do not heed the warning. But otherwise today, using space technology, using satellites orbiting at various altitudes from beyond Earth, it is possible to make different measurements of those signals which you can pick up in visible, infrared, microwave, and use all of this to put it in weather models and predict how the weather is going to change, etc. Here again, you need to appreciate, normally one gets a feeling that in temperate zone, weather prediction is very good, but in tropical zones like India, equatorial zones, the weather prediction is not that good. Here, it's a technological problem because the number of variables which impact the weather is much larger in the tropical and equatorial region compared to temperate zone. That's why the models perform much better in temperate zone. And for tropical zones, you require a lot more observations. So that's how slowly things are improving. But today you can definitely see that India, with its ability to build this space technology, is giving early warning to disaster relief agencies who are in turn actually evacuating the people to safe zones and save their lives. In a similar manner, other important development that happened with the space technology availability was actually, you can say, from broadcasting, communication, weather monitoring, and also on resources, earth resource monitoring or remote sensing. India started using satellites built and by observing earth, the various aspects, water bodies, and then fault lines, lineaments, geological features, and then making observations in many different wavelengths. You can easily see that if you are able to put a satellite orbiting an Earth, then what it can do is there are no boundaries for it. It can cover the entire globe depending on what type of orbit you choose. You can choose an orbit which is closer to Earth and it can be inclined to equatorial plane or it can be perpendicular to equatorial plane. You will hear about this during some of the talks in a subsequent special talk. But right now, I just want you to become aware that the way you can put an object into space is you take an object beyond Earth's surface to a height, and at that height, in a specific direction, if you give a specific velocity called critical velocity, then that object will go around Earth in a circular orbit. If you give more than the critical velocity, the point of release becomes the perigee, and the other side it will go farther, and it is called apogee. But if you put a velocity less than the critical velocity, the point where you release can become the apogee, and the other side, depending on how much is the less velocity, it could even go and hit the surface of the Earth. So depending on that, you can put the satellites in different orbits, different inclination. And if you choose an orbit at 36,000 kilometers, it takes exactly 24 hours, which is equivalent to the time Earth takes to rotate about its own axis. So as a result of that, you can do. So in this, you can see a person like Dr. Sarabhai who visualized how an advanced technology of building rockets, building satellites, taking it to space can make a difference to the life of the country, though it was a fledgling democracy struggling to provide solutions in limited resources. India demonstrated that using this space technology address these problems which will help rapid development in the country. Many things including remote classrooms, telemedicine also became possible because space technology was used to provide. What is telemedicine? Before in fact, decades back, India used a satellite called EduSat, wherein you could connect a person, a patient from a remote place like Andaman Nicobar or even within the mainland, some remote places. They could be linked to the super specialty hospitals via satellite, and then the health monitoring of the patient, the information could reach the super specialty hospital doctor, and then through this process reduce the task of transporting the patient to the mainland or to the super specialty hospital, and only many of them could be treated like this, but some of them, if when they need, of course they have to be transported. That was being done. So space technology India started using for addressing the problems it was facing of communication, broadcasting, then weather monitoring, and even earth resources monitoring. It's also possible to tell ahead of harvesting what is the crop yield this year, and then whether the crop is going to be bountiful or is there going to be shortage. And even to the extent today it is possible to tell what is the soil moisture, and then how you can do preferential treatment to the different portions of the agricultural field to take care of what micronutrients are not shortage there. So a whole lot of things are being done. So what India did, it started with the site program, and step by step it built its capability of putting a satellite launch vehicle. Abdul Kalam was the first project director of a satellite launch vehicle which was attempting to put a 40 kg satellite into orbit. Of course, the first attempt failed, and you are also very familiar that when this failure occurred, how Satish Dhawan actually, in a way, handled the situation to make the project director Abdul Kalam. He has also written this in his book that when the first press meet happened, Satish Dhawan, in fact, went and took the press briefing. He, in a way, told Kalam that you be here, I'll face the questions from the press. Next time, when the launch became successful, the second attempt, he said he sent Abdul Kalam to the press meet and he stayed behind. So basically, here, what you need to see as an organization, how to deal with failures. Now you can easily visualize that if you want to do perform a task which you are assured is going to succeed 100%, then what is the nature of the task you will take? Obviously, you will remain within your current knowledge and skill, because if you are trying to attempt anything beyond that, there is an uncertainty and you are not sure whether the outcome will be favorable or not. But then you also see, if you want to make sure everything you are doing is 100% successful, you are not pushing yourself beyond your current limits of knowledge and skill. But if you remain like that, can you achieve anything new? Can you bring any new thing into reality? This is where the problem comes. So unless you push yourself beyond your current knowledge and skill, you cannot do something which others have not done so far. So that means the task of building launch vehicles, satellites, for us in India at that time, if you visualize, unlike today, information is not easily accessible. And also because of the nature of space activity being dual use, information is not easily shared. So that means people are working here beyond their current knowledge and skill, and they are trying to make things happen. So at that time, obviously, it is quite possible that you will encounter failures. But then, if you are prepared for dealing with that failure by identifying what went wrong and how to rectify, you will succeed in the next attempt. That's how, even in the SLV-1, when Abdul Kalam was working, the first, he was the project director of that program. First one was a failure, second one was a success. Similarly, in even PSLV and some other things also, it similar happened. So here I want you to primarily appreciate this idea that if you do not do anything to push your own current boundaries of knowledge and skill, you cannot do something which others have not done or which you have not done so far. But when you are attempting to do that, you are more likely to encounter inadequacies and failures than attempt success in the very first attempt. So because of that, you will also prepare yourself well for dealing with failure. And if this ability of dealing with failures, which has made a difference in ISRO over a period of time, and it has always been attempting to push the boundaries. See, like I said, when it was a fledgling democracy, nobody was looking at how to make use of space technology for a developing country's problems. India pushed it, and then it step by step learned the task of using this technology. And you starting with INSAT series. In fact, INSAT also, when it was conceived, it was a very unique program. At that point of time, nobody had put in a single satellite all the components of broadcasting, communication, and weather monitoring in a single satellite. We had to do that because we could not afford three independent launchers and three independent satellites. So the Department of Space and ISRO configured such a satellite INSAT and then got it launched, and it became in a way trailblazer later, and then it went ahead. So then similarly in remote sensing, India started its program of using accessible technology for understanding, and then started building its own sensors of Indian remote sensing satellite, starting with Bhaskara, which provided a 300 kilometer by 300 kilometer frame image with 1 kilometer resolution, and gradually step by step today we have imaging systems which can provide as good as 30 centimeter resolution at many different time scales and spatial scales. So you have a sensor called ocean. In fact, this is another very interesting thing. Like, remember I told you that Dr. Sarabhai had to convince the fishermen for conducting the initial sounding rocket experiments. So what India did in 1999, using a satellite called OceanSat, by looking at the color of the ocean from the orbiting satellite, the scientists found out how this color can tell where the chlorophyll is, and the chlorophyll, through chlorophyll, identify the food chain of the fish, and through that tell the fisherman where in the ocean if he goes, he is assured of a fish catch. Now you can imagine India has a coastline of 11,500 kilometers, and lakhs of fishermen depend on their livelihood for catching fish. Now, if they are aware where they can get fish, they will directly reach that place, and they will spend less on petrol and diesel. And this saving on petrol and diesel can provide, is providing in India almost 10 to 15,000 crores saving. What is being done? Using this ocean sat, you are able to tell what is called prospective fishing zone. That means where the fisherman is likely to get a good catch of fish. And not only that, with our navigation and communication capabilities, today one more thing has been done. That is, you have a battery operated gadget which is fitted into the boat of the fisherman, and this gadget communicates with a mobile in the hands of the fisherman. Now you will also realize any mobile which is few hundred meters, 500 meters away from any terrestrial tower will not get any signal. But then this mobile communicates with the gadget put in the boat of the fisherman through our navigation and other satellite mechanism. It is there is an app in the mobile which, using this information, shows in a video compass mode where the fisherman has to go for catching his fish. Not only that, it gives him an alert in his mother tongue about the weather vagaries. If the sea state roughness is going to be unbearable, or winds, thunderstorms, and then cyclonic storms are going to affect the stay in the ocean. All this will be given as a warning in the mobile, in the mother tongue of the fisherman. And also, many times our neighboring countries capture the fishermen because they wade into the international water. Even that, this gadget mobile app alerts him saying he is approaching international boundary, and then he needs to be careful. So you can see here the example of a person who does not know reading or writing is making use of the most advanced technology of satellite put into space by a rocket, and with application and other facilities, alerting the person how to carry on his livelihood. So a person who does not know reading or writing is also getting benefited from space technology. Today, more than 1 lakh such gadgets have been built by industry today and is being distributed to the fishermen across the country. So in all this, you can see India started making use of space technology for addressing the specific problems it was facing of broadcasting, remote classroom, teleeducation, communication, weather monitoring, and also resource monitoring. And in resource monitoring also, today for many crop types, it is possible to tell before harvesting what is the yield of the crop, whether it is uh, wheat, rice, sugarcane, cotton, jowar, groundnut, you name it, jute, many of them. And there is a center in Delhi called Crop Mahalanobis Crop Forecasting Center, which making use of satellite data provides inputs to the various stakeholders. In a similar manner, today ISRO also works with many space other agencies across the country. And here again, you can see ISRO or Department of Space pioneered the use of space technology for various activities in the country. Today, you will also be happy to learn that many of the governments and the government systems make intense use of the data generated from satellites, and using that, they are able to improve the governance. Just to give you a couple of things that had happened in the past. See, when many of the state governments were dis actually disbursing funds for building houses, the mechanism of using a mobile and ability to take picture and locating that picture with a time and space marked on it made sure that people could actually submit their applications for the progress that is happening in the construction of the housing, and using that with very little effort getting the approval for the further sanction. And you also know in the actually Manrega program, lot of states make use of large amount of funding for building various infrastructure. So now, with last many years, what the space-based observation is helping is all these are getting monitored, and then through various crowdsourcing methods, the specific activity that happens under Manrega gets monitored. It comes into a database, and using such database, more than 4 crore assets have come into the database. And similarly, there is a thing called space-based information system for panchayat or planning. And here also, lot of information is getting generated and then being provided to the various Panchayat Raj institutions. And ISRO developed this technological capability of starting from satellite launch vehicle, which could put 40 kgs into orbit. Then it went to hundreds of kgs, thousands and tons. Now it is capable of putting satellites into LEO, GEO, even lunar orbit and Mars orbit. And each one of them is a technological skill and capability which has demonstrated that India is actually not only using the advanced technology for addressing the problems it is facing, but also it is using it in very novel ways. For example, when India did its Chandrayaan 1 program, you are aware that though at that time man had landed on the moon, it is Chandrayaan 1 which gets the credit for discovering the presence of water molecule on moon and the process of water molecule formation. Similarly, when Mars orbiter mission orbited the Mars, India became the first country in its maiden attempt to achieve such a success. And then last year, a couple of things happened which I would like to draw your attention just to bring to your awareness how people recognize you for your demonstrated competence. That means people don't recognize you just for your claimed competence. Like I said, site experiment, we borrowed an American satellite in 1975 and used it for 1 year. Last year, August 1st, exactly 50 years later, India launched a satellite called NASA-ISRO Synthetic Aperture Radar. This is one of the most advanced technology satellite which is able to make observation of the entire Earth twice in 12 days, and it can generate information about surface deformation, biomass estimation, and then even cryosphere, a whole lot of observations it can do. India and America worked together on this mission. This is almost a $1.5 billion project where India spent only 10% of it, America spent 90%. But this payload, which carries an advanced technology SAR called Sweep SAR, was built the payload was built at JPL with one component coming from India, an L-band portion of the SAR from India. But this payload is fitted in our satellite and we launched it last year. So you can see an highly advanced technology satellite. America was ready to trust India for launching. How did it happen? It did not happen overnight. It happened because India demonstrated through Chandrayaan, Mars mission, and also a number of radar satellites we had built our own. Using that, then they were ready to work with us for a common program. Similarly, last year, one of the American firms launched its what is called as a Bluebird, a satellite which contains 40 feet by 60 feet size antenna after it is deployed in space. That means again it is one of the most advanced technology communication satellites built by an American private company. They were also ready to risk their launch on an Indian launcher. So you can see India over a period of time has built a capability of building launch vehicles and then making it work and gain the confidence of the global community. Similarly, when you launch 104 satellites in one go and then provided satellite for South Asia application, a whole lot of them are there. You will learn during the course of your this week where many people are going to talk. You will hear many of them. But what I want to bring to your awareness is a broad picture. India started using space technology not for the intention of developing technology per se, but with the prime objective of using this technology to rapidly change the living conditions in India so that India's progress can be hastened. This happened through, like I said, using whatever technology is accessible you use, what is not accessible you build your own, and then step by step move ahead. So with this broadcasting, communication, then when navigation became a problem because of the Kargil time, India started developing its own regional navigation system. And then India also had the privilege of doing something very unique. Between 95 and 99, the India had the privilege of saying that in the civilian domain, highest spatial resolution image are generated by our satellites. In fact, this helped India to put almost 18 ground stations across the globe, and globe was receiving this data. Later, of course, the other private companies came up, Iconos and many others, so who built high resolution imageries even in civilian domain. But then, if you look at the way India has progressed, it has made the most optimal use of its resources. And when something was denied to it, it developed its own. Best examples are the cryogenic engine itself. While one superpower was ready to give the technology, another superpower ensured that it did not happen. But then it was a blessing in disguise. Today, we have more than three versions of the cryogenic engine, which can be taking our satellites to different orbits, GEO, LEO, and a whole lot of this. And then, like I said, when we started the space journey, we were a fledgling democracy, low down in the economic order. But today, we have reached an economic position which is the fourth largest economy, and very soon it should become the third, second, and aspiring to reach also the topmost position by 2047, that is 100 years of our independence. Now, if that has to happen, whole lot of things have to be done. And then beyond that, you also need to appreciate that every technological capability also brings in a new tool in the hands of the man. And going to space, humans in space is again a very important capability. And India also, having realized that during the nuclear events, that because India did not do certain activities at a certain point of time, we were not able to be part of an international dialogue on nuclear proliferation, non-proliferation, etc. So, in a in a way, you can say to prevent such things from happening, India is now opening up its space sector to not only private sector but also enabling India to take advantage of the developments that have happened in space technology. Man in space is also a very important aspect. So India is already working on this, and in next couple of years you should see Gagannauts going around Earth, and then by 2035 have our own space station, and then beyond the space station by 2040 landing on moon. Now, in a way, if you see the what is happening globally, there is a lot of interest on moon and Mars, Venus, etc. All this because humanity wants to understand the universe. Understanding the universe makes making more observations and more sensitive and more detailed observation. So human being has been doing this all the time. If you go back in time, when you look up at sky, humans realize that the sun and moon move in the sky in the backdrop of the star patterns. And if you are able to correlate star patterns, then you can understand how the events are happening, how to correlate events, whether it is rainy season or seasonal changes, etc. So they started building that observational capabilities and then started understanding the universe. Today, if you want to look at space from Earth, you are inhibited by the atmosphere. Atmosphere, if it is cloudy, you cannot see anything invisible. But if you go beyond the visible wavelength region, there are certain wavelength region where clouds can be transparent. In fact, we use them for making observation from microwave sensors. But then if you want to make more and more sensitive observation of the celestial object, then if you can do it beyond Earth's boundary, Earth's atmosphere, then you can get better sensitivity. That is how others did Hubble as well as James Webb, but India also did. You will be happy to know that India started a space science program way back in 75 with Aryabhatta itself, but it has made use of all opportunities to build this scientific observation capability. And today, with our own astrosat, actually astrosat has operates a telescope which has the highest angular resolution in a specific wavelength, ultraviolet, and also higher sensitivity. Using this, our scientists are getting virgin data for doing research. And then Aditya also is looking constantly at sun. So in this manner, what India did was started using an advanced technology for addressing the problems we are facing on a day-to-day basis. Today, the availability of space-based capability of communication, broadcasting, navigation, resource monitoring, a whole lot of things, all of them have become a possibility because India started addressing these problems from the fundamentals. And also here, two things you need to remember. Dr. Sarabhai had said we should be second to none in using the most advanced technology for addressing the problems facing the society. But then not only that, using this when the Indian capability went on improving, today you can easily realize that we have such friendly neighbors, we cannot but use our space capability to understand what is happening beyond the borders. That means space also needs to be used for preventing or providing sufficient information to the strategic user community for dealing with the problems you are going to face. And in a similar manner, putting man in space is also an important requirement. And space is going to be more than $1 trillion economy shortly. In India, a country which is capable of building end to end, from launch vehicle to satellite to sensors and application, should it not gain a significant portion of the space economy? That's where the government is making changes in the rules and operation, encouraging more and more private entities and academic institutions to contribute. And it is here that you come into picture. If academic institutions have to build a capability, who are the actual performers of those tasks? They are the next generation students. And if next generation students at an early point in their life start appreciating what is happening in space, how things are being done, then trigger some of the thought processes in their mind that can they make a difference to what is happening. And as you can visualize, it is the innate curiosity of the human system that has driven technological development. Human being all the time is trying to look at how to enhance the limitations of the sensors he has, limitations of the actuators which is available to him, through which he is building greater and greater capability. Just to put point in perspective, if you were to think of how much can a human being walk in an hour, obviously we'll say he can walk 5 to 6 kilometers. But then what all did he do to transport himself on land much faster than this? He realized that there were other animals moving faster than him. So he domesticated and started riding them. He saw birds flying. So today he has built aviation machines which can take you. So rockets to take you beyond Earth. And then similarly, your eye has a limited visual capability of looking at objects when only sunlight is there to start with. But then he gradually realized that he can build artificial sources of light. Not only that, he can also make sure build gadgets which can show him what is happening beyond the visible wavelength, like an infrared camera or a bat-based radar or sonar. So like this, technology, all the technology is inspired by nature. So if we are able to communicate to our next generation that each of them have a tremendous possibility of using their sensors and the intelligence which is operating within them, the kind of problems they can solve by taking inspiration from nature can be phenomenal. And it is here all of you have a task by looking at how India has done in various areas, and then how can we tell this in a story form, and through the story attract their attention and also challenge them of addressing problems, newer problems, and solving them. And so in this mode, if you look at few points what I want to just bring to your awareness again is India started its space journey with the primary objective of addressing primarily the problems it was facing of communication, broadcasting, weather monitoring, providing access to information for governance, a whole lot of this. But then as you keep building, you also need to realize that the people who are in this task needs to be challenged to remain contemporary or competitive. That is why space science programs became relevant. India started its work on lunar mission, Mars mission, and then a host of others. And then slowly building consensus among the user community to use the space technology for various activities. And this also has taken different speeds with different entities. But then all of them are moving towards that and it is going ahead. And if you remain within the confines of current knowledge and skill, you cannot perform anything which is not present already. So that means you need to push yourself beyond your current boundaries. And if you are pushing yourself beyond your current boundaries, naturally you are likely to fail. That means learning to deal with failures becomes an essential training program. And with that, you succeed and with subsequent steps. You can see how India dealt with Chandrayaan 2 failure, and next time when it attempted in 2023, it demonstrated to the world and reached a place on moon where nobody else had gone. You also will recall around that time how many others attempted to reach there and none of them succeeded. And even later, a couple of them who reached there had their missions in some way impacted. So in all this, the lesson for us is the Indian minds and Indian capabilities is enormous. But if you challenge them, then they can deliver. And you need to keep yourself pushed beyond your current boundaries if you have to make a difference or if you have to make an impact both within the country and outside. So with these basic perspective of using space technology for national development, and here concepts like leapfrogging also comes into picture, and then going beyond what others have done, and in doing, pushing yourself beyond your current limit and learning to deal with failures, all of this, and then teamwork, all of these are essential components of successful making. So you have a task on hand. Your task is to tell the story to the next generation, not only inspire them of what has happened, but then show to them there's a huge challenge ahead. See, if you have to build space stations, you have to build the astronauts or juggernauts going, then life beyond Earth, there's a whole lot of areas in which work can happen. So bringing in projects and then making use of those through the projects provide experiential learning to the students should be our way of attempting to bring them awareness. So I'll stop here and I'll take any questions that you may have. Thank you very much for the patient hearing and wish you a very successful week of increasing your awareness to make the students become more capable.
Thank you, sir, for such an exciting talk. You have summarized vast canvas of technology and application to the participant of all the school teachers, and that to summarizing into such a big canvas into a 1 hour talk always is challenging, but we found that you have excellently did it, and I can see a lot of response from the audience. I mean, the teachers, and they have appreciated a lot your talk, and they have asked many questions. In fact, it's difficult to take all questions. Otherwise, it will again take 1 hour talk on that. So I would take a selective few one for you to sir explain them. One I found Seema Sancheti. She is asking, with the rapid increase of commercial satellite in low Earth orbit, what do you think is the most sustainable approach for managing orbital congestion and space debris at basic level?
Yeah, very good question. In fact, here again, you need to see how humanity progresses. First thing is you want to achieve something. At that time, the idea is, can we go to space? That at that time you are not worried about what are all the consequences. Your first desire is to go to space. Then you start looking at, now having gone to space, how can I use it effectively? Then for users, you start bringing in systems. But then as you keep doing it, you encounter problems. And then now you start addressing those problems. So in this context only, when humanity started looking at space, they were not concerned about whether there is going to be debris, there is going to be traffic management problem, etc. But then as they started operating, they realized we need to put more and more satellites into orbit. First, this problem came in the geostationary orbit, because in geostationary orbit, if the entire globe or all the countries had to be supported, the under the United Nations, there is an entity called ITU, International Telecommunication Union, which in a way started actually coordinating for providing slots in the geostationary orbit. And for this, they said, once your job is over in a geostationary orbit, you should not remain in that place. You should push your satellite beyond that orbit. Like in a road, see, if you keep a non-moving vehicle on the road, it becomes an obstacle. So in same way, non-functional systems occupying space is not good. So then the idea of graveyard orbits came. That means the satellites, those who are putting geostationary satellites, after their functional usage, were asked to remove it from that location, go to a higher orbit, so that that space become available. Now today, low Earth orbit is becoming congested because people, in their desire to provide, for example, internet communication to the entire globe, people are talking about 42,000 satellite constellation. Already thousands of satellites are operating in orbit. And each of them can be a potential threat to the other satellite, like traffic management. You are going on the road and there are multiple vehicles. Unless you know how to manage your traverse without hitting the other object, that is the traffic management on ground. Same way, space traffic management is becoming an important topic. Now, slowly consensus are emerging. All those new satellites which are being built are being demanded after your functional usage. Don't leave it there. Bring it to a position where they can decay rapidly and then come down to Earth. So normally 500 kilometer and below, if you take, they don't survive long if you do not maintain the orbit. Then again, this is a problem. Sometimes you lose track of, you lose control. So people are now looking at, can we scavenge them? That means now there is a new set of entrepreneurs who are coming up, who are thinking of how can we grab these satellites and take them out. Now waste to wealth, like a ship being broken and using the spare parts for other things. People are looking at, can we capture these and then take out parts and make them available for other satellites, repairing satellites. So all this is becoming a natural consequence. And you can also visualize these are step-by-step activities. First was desire to make something happen. And then as that desire becomes in a way operational, it poses problems. You start addressing them. And as the economics of doing that becomes viable, you will see many companies doing this task of space scavenging, removing things, refueling them. All of this will come into picture. And here is where there is also a lot of challenge for the next generation to come up with innovative solutions to that.
Thank you, sir. And there are many responses of appreciating your this thing. I'll just read one. Somebody writes, excellent storytelling, sir, inspiring, informative. I will bring this to my students. The next question, sir, I will take written by the Anupam Saha. He's asking, sir, as you mentioned, selecting a location near geomagnetic equator, that location was considered at the time. Could you kindly explain the reason for this requirement?
Okay. See, at that point in time, you can see this cosmic ray observation and then understanding upper atmosphere by conducting specific experiments. See, otherwise, all the methods that were being used were, even if you take electromagnetic radiation, ionosphere behavior, or cosmic ray studies, etc., required understanding of what is happening in the various locations at different heights from the Earth's surface. So sounding rockets had a capability of going between 20 to 40 kilometers, and it would carry some sensors, and using those sensors, it can do some in situ measurements. And this was what was being done. So geomagnetic equator in a way gives a unique location, because at that place, if you do the find what is happening in the upper atmosphere, it adds a new information set to the contemporary dialogue of understanding the atmosphere. So that's how Dr. Sarabhai and the team visualize that if through a sounding rocket you release some kind of a material which will spread based on the like sodium ion vapor, etc. So then by imaging them, by looking at them, you can find out certain patterns of the wind and also certain parameters. If you measure, it adds to the scientific knowledge base. So obviously when you are looking at some new way of doing things, people get excited. So the scientists also appreciated that over geomagnetic equator doing such an experiment is useful. That's how they were ready to share the both the launch, the sounding rockets, as well as some of the instruments that can be carried on that.
Thank you, sir. The ne- Hello, sir. Am I
Yeah,
audible?
yeah, you are audible. Go ahead.
Okay, sir. So another question is by Ankush Ashoka. What speed is a geostationary satellite moves?
Okay. See, now if you look at any object, depending on the distance at which it is traveling, the farther and farther, it's you can easily calculate the relative velocity, or the angular velocity is known to you at 36,000 kilometer from the surface. The if the satellite is moving, then r omega you take, then you will get the velocity. You can calculate. Low right now, I don't remember the exact number, but it is less than maybe 5 kilometers per second, etc. Close to Earth's orbit, it is 7.5 kilometers per second. But at 36,000 kilometers, the velocity of the object will be slightly slower.
Okay. Okay, sir. The another question somebody wants to know about ISRO's development plan on Mangalyaan 2.
Yeah. Okay. So here the Mangalyaan 2, primarily one of the objectives will be do something beyond what was done in Mangalyaan 1. In Mangalyaan 1, we only did an orbital instrument, and in Mangalyaan 2, the one of the prime objectives will be to touch down on the surface and do some in situ observations also. And then, of course, this is still in the process of getting firmed up on the final the activities that will be done on that. It's one of the many space science missions which is in the horizon, and the exact definition and exact project formulation is still to happen.
Okay, sir. So one more question is like, what is the average lifespan of a satellite? Can we recycle a satellite?
Yeah, see, that is one of the things now. What limits the life of a satellite? If you look at what is it that you are trying to do? You have an object in space which is moving around. Now, if that object has to be useful for you on Earth, two important things are there. One is you should be able to communicate with that satellite. That means you should be able to establish effective communication. Then, whatever function that satellite is performing, that information you should be able to send to ground. So that means functional outcome should be reaching you, and you should be able to control its orientation. Now, when the satellite is operating like this, if its orientation cannot be controlled, it will become useless. So that is where one of the thing is how to maintain the orientation of the satellite becomes important. For that, typically what we do in most of the cases, you have got small nozzles or thrusters through which you can fire and change the direction. But there are objects called reaction wheel and momentum wheel. Using a gyroscopic principle, you make a particular axis of the satellite very rigid. That means it doesn't get disturbed. But whenever such disturbance happens, you compensate it by the reaction wheel, and then you offset again by doing one firing. But how much of fuel you are carrying is stored in a bottle. Once the gas or the fuel you are carried is exhausted, you cannot control the satellite. So similarly, there are solar power required for operating. If the power generation requires rotation of the panel, any moving mechanism can have a finite life. And then there is also every satellite goes through an eclipse. During this eclipse period, there is a battery which is supporting the life operation of the satellite in the absence of solar power. Each battery also has a the number of cycles through which you can go through. So these are the life limiting things. And then any system, if it fails, some redundancy is built in. Using redundancy, you can take care. But then you can build satellites to operate up to 15 years. All geostationary satellites have a typical life of 15 years. Low Earth orbiting satellites are built typically with a life of 3 to 5 years. But then by specific effort, you can increase the life or make use of it for a longer period. But you have to pay penalty for the extra resources you are putting. And in terms of recycling, when you are saying, there are already companies which are now building mechanism for refueling. That means if the fuel is exhausted, you can refuel and use it. And you also may recall Hubble did a repair job in space and then rectified a problem. So in principle, all of these are possible, but whether it will happen or not depends on the economy of doing it. See, if the cost of repairing becomes much more than replacing a fresh one, what would you prefer? So that's how things will go. But then there is also the risk of debris left leaving, etc. So by different ways, the attempts will be done to deal with the situation. These are all problems which is actually at the heart of many interspace agencies and UN bodies, which is trying to look at how space activities can be kept sustainable so that they do not become unviable. So if that has to happen, everybody has to cooperate, and these activities are also going on.
Thank you, sir. Actually, there are many questions, and few of them are related to some asking more details what you have already told them. So instead of taking all
Probably
questions,
you should tell much of them will become available during the course of many talks that are scheduled.
and we are also thinking, sir, to compile all these questions and write some answers and share these
Yeah,
people in the end. So
correct.
because taking all questions will be difficult, but I would like to take one
Yeah,
more question, sir. Last question.
sure.
Somebody is
Okay.
asking, how do sensor work from distance, and how does radiation help to track algal bloom and ocean color?
First one was again repeat. First
How do
question.
sensor work from distance? From distance, how they are
Work,
able to detect?
work is it?
Work, yeah. I mean, it's something like principle of remote sensing or something. How sensor work from a
Okay.
distance?
Yeah, okay. Only from distance, if you say it is different. But if they're talking about work, then it has to be something more. Okay, let
He
me
writes,
attempt.
how do sensor work from
Work.
distance?
Okay, okay. Then it's clear. All right. So it is very clear. See, now, for example, you take a human being itself. When you are seeing things, are you seeing things with your eye in contact with the object? Object is illuminated and that object is visible to you. So your eye is also operating in an electromagnetic radiation, and that radiation scattered or reflected from the object is reaching your eye, and through the eye as a sensor, within you there is a processing system which is interpreting it. So what we do also is very similar. When you take a camera from a mobile, what is happening? In the mobile, there is a lens and also a detector. The scene is captured in the detector, and that is converted into digital information, and then that digital information is converted into a display device, and it is shown on a screen, or it is converted into data. That means, in a way, humans also have non-contact sensors. Now you can visualize yourself what are those non-contact sensors. And then remote sensing is nothing but observing from a distance, and then using, for example, like I said, I can see only 400 to 700 nanometers. But you know, today, electromagnetic radiation occupies a wide range of wavelengths. So humans have built X-rays, infrared camera, ultraviolet camera, radar, a whole lot of instruments to show you what is happening in nature in a wavelength in which your eye could not have seen. So that means you are actually enhancing your ability to make observation by building sensors. And all these sensors are in a way operating from a distance only. So they are not physically in contact. This is the difference. In situ remote sensing, when you say you are actually in contact with the object. For example, when we did our the spectrometer or the LIBS activity, that laser induced ablation experiment on Chandrayaan 1. The rover carried this instrument, a laser fired the surface, and some evaporation happened. And in that evaporation, using a spectrometer, you picked up different wavelengths. So this is in a way an in situ observation of what is present physically through contact. Temperature, if you look at again, thermometer, when it is in contact, it's a contact sensor. But if you measure infrared radiation and correlate the temperature, it becomes a non-contact measurement.
Thank you, sir. Next question was the algal bloom. How they detect algal?
Yeah. Okay. See now, for example, what we have is ocean color sensor. These ocean color sensors, they are observing the ocean in many different wavelengths. Now, when this algal bloom occurs, that manifests in a specific wavelength coming out from the surface of water, which is picked up by the satellite, and then it displays it as an image. So you can see wherever there are algal blooms, you can identify its location, and it also I can identify its pattern, its extent. So basically, if you are able to identify any feature with a parameter which can be measured, you can do that measurement. Chlorophyll, like I said, you can make chlorophyll, but then using chlorophyll, how we reach fish is looking at the food chain of the fish. What eats a chlorophyll, what eats that zooplankton, etc., etc. So that means some is direct measurement, other is inferences in a systematic manner.
Thank you, sir. And now I close this question and answer session, and we will see that all other questions written there, we'll reply them in a future course of action or through a written reply. We'll take care of it. And please do ask question in all the sessions. And I take this opportunity to thank Kiran Kumar sir for giving us his precious time today. Although I knew he was busy in the morning, and he take out his time for this particular talk, and I see a huge response of the many teachers appreciating the talk, sir. So thank you very much, sir, for joining this thing.
Thank you very much, and wish you all the very best. Keep pursuing this and make it happen in a more and more dynamic way. Thank you.
Thank you, sir. And now I think organizers next talk would be at 4 o'clock in the afternoon. So we close here and we'll again join you in the afternoon at 4 o'clock for the next talk. Thank you very much.
Thank you.